Okay. Parallel. What's this? 7. Okay. This is just like series, the same slides as series, except voltage is common instead of current. We're still finding X of L, X of C the same way. In fact, we didn't even do that this class because we did that previously, right? Okay. So to find impedance total here, you can either do product over sum, or the admittance method, or if you want to add all the currents up, find the current here, find the current there, add those two things up to get impedance, current total. You've got a voltage, find Z total that way. Okay. All right. Current's additive in parallel, so we can use a triangle. Okay, line current can be found using Ohm's law. If you get impedance total first, then you can just divide voltage by ohms to get total current. Okay. Admittance method. In other words, get R to the R branch, take the reciprocal, add that to B sub L. That's this, right? In rectangular form, put it in bullet form, take the reciprocal of it to get impedance total. Okay, conductance can be found. You can do the cosine of negative 59 times y total, or how would we find conductance here? That's it. It's easy enough. Okay. Okay, converting the parallel LR circuit to a series circuit, three things have to be the same: current, impedance, admittance. Fair enough? All right, so we find a Z total, and we break it out to rectangular. I'm going to make a parallel to a series. Then once I get a Z total, if I break it out to rectangular, there are my two values. Okay, 2 pi FL to find what the inductor's value has to be at 100 kHz. Okay. Here, if you're asked to add some component in parallel, we're just going to cancel out the 3K. Put the 3K in parallel. 1 over 2 pi FC to find what the value of that capacitor is at that frequency. Fair enough? We're doing it the long way here to get B sub C. But then once you get B sub C, you have to reciprocate it to find out what X sub C is. All right, and then plug it into 1 over 2 pi FC. Here we're canceling out ohms. Okay, the whole point of this is to cancel out any reactance to make the circuit act purely resistive. We do that by either changing the frequency, 1 over 2 pi square root of LC, or power factor correction. Okay, calculate the value of parallel resistance and inductance for a circuit given the values of line current, generator frequency, and generator voltage. So if this is parallel, if this is in the box, I've got a parallel circuit, and I know current total, and I know voltage total. What can I do here? I can do Ohm's law, but if current is additive in parallel, yes? Can I just break the current out in rectangular form and find out what's in there? Okay, we do Ohm's law here, and you get Y total. Find that out. Put it in rectangular form to get X of R, the R in parallel, and X of L in parallel. Parallel current method, get the current, which is given, 25 milliamps, break it apart, and there you go. There it is. That's the way I would do it. All right, and here, all we're showing you here is that if you have a current at one branch and a current at the other branch, this is at negative 90. You've got a voltage and you've got two currents. You can find a resistor and a reactance. Okay, compute AC electrical parameters for a parallel RC circuit. This is all the same thing except with the capacitor. Okay, X of C is at negative 90 degrees. And now converting it to a series equivalent, we're adding ohms, get Z total, break it out into the rectangular here to get our series equivalent circuit. Okay, compute AC electrical parameters for an LCR circuit. Again, same thing, we're adding Siemens and we're adding current in parallel. Okay. I know it's tough, just hang in there, we're almost done to the end of it. We're almost at the end of this one. All right, depending on how the circuit is acting, you only have two components that represent whatever is in that box. Okay, power factor correctors. Okay, to make total X of L smaller, I'm going to put the inductor where? In parallel. Yep. And if I want to make X of C bigger, I want to make X of C equal 8K, I've got to make capacitance what? Y'all remember this one? Where did we add the capacitor? Well, that would make X of C smaller. And I have to put it in series. Okay. All right, any questions on this class, on this lesson? All right, let's take 15, be back here at 14:15. Angular, and we're off and running. There we go. Total impedance. And then line current, Ohm's law, times or voltage divided by impedance, get current. Line current flows through R1, X of C1, X of L1, X of C2, and total box in here, right? So here we're finding all of our voltages, EO1, voltage of C2, and the voltage of this CEQ. Okay, and there's assume voltage. I'm not going to run through it. Everybody knows how to assume a voltage, assume current, correction factor, and multiply, yes? All right. Any questions? Series parallel. All right. It's all the same thing except we're doing a correction factor. We get to the end, get a voltage assumed, current assumed. You still get your real impedance, and you get your correction factor, and then multiply by everything to get your real values. Okay.